Cell 1. In this segment, we delve into the critical rationale behind an energy company or government taking the proactive step of trimming trees. This practice isn't merely about aesthetics, it plays a vital role in maintaining the integrity of our power systems and ensuring public safety. By preventing trees and branches from coming into contact with overhead lines, utilities can significantly reduce the risk of power outages, especially during storms, as most outages stem from such contacts rather than pole failures. Moreover, should an outage occur, the speed of restoration becomes paramount. With fewer trees downed, utility crews can navigate blocked routes more quickly, which leads to shorter power restoration times. This is essential for maintaining public safety, as fallen trees pose various dangers, such as potential electrocution, fire risks, and impediments to emergency services. By keeping high risk corridors clear, emergency responders like ambulances and fire trucks can operate efficiently, ensuring that critical services remain uninterrupted. The financial implications are also significant. While it may appear costly to engage in regular tree trimming, neglecting this task can lead to exorbitant emergency repair costs. In emergencies, expenses can soar into the millions, especially when considering overtime pay, logistics, and necessary coordination with local authorities. The repair needs go beyond simply fixing downed lines. Often, extensive work is required, such as replacing poles, transformers, and clearing vegetation under hazardous conditions. Additionally, unplanned outages can disrupt not only power supply, but also ripple through the economy, affecting businesses, hospitals, and even traffic systems. The consequences can be dire, from spoiled food and lost wages to critical medical device failures. One tree falling can initiate a domino effect, causing widespread grid instability and further outages. As we progress into the next cell, we'll likely explore more about the specific methodologies used in tree trimming and maintenance, emphasizing how systematic approaches can enhance overall electrical reliability while minimizing risks. Cell 2. In this cell, we're diving into the setup for a complex analysis focused on urban forestry risk, specifically in the context of Charlotte, North Carolina, and its suburbs. By utilizing several powerful Python libraries, we're laying down the groundwork for generating synthetic urban elements and assessing the related risks associated with trees in urban environments. To start, we'll import essential libraries like NumPy and Pandas, which are fundamental for numerical and data manipulation tasks. Next, we'll include Shapely and GeoPandas to handle spatial data effectively, allowing us to manage geometric objects like roads and tree locations. Folium and Plotly will enable us to create interactive maps and visualizations to present our findings compellingly. This integration of tools ensures that we can not only generate the data, but also visualize it clearly. The main logic revolves around creating a synthetic representation of a road network that mimics the highways and local streets you'd find in the target area. We'll also generate points representing tree inventories near these roads, particularly focusing on areas around hypothetical power line corridors for added context. The goal here is to compute a storm risk score, which will help us evaluate the probability of storm damage to urban forestry. Moreover, we'll aggregate these risks by neighborhood or zip code, providing a clearer picture of where the highest risks lie. Features such as distance to roads or power lines, tree health, species type, and environmental conditions like soil saturation or wind exposure will provide valuable insights into the factors that contribute to tree vulnerability. It's important to note that assumptions regarding urban density and tree distribution play a significant role in accuracy, as these can heavily influence the outcome of our risk models. Moving forward, in the next cell, we'll likely build upon this foundational analysis by delving into the actual computations of our risk scores and visualizing the high-risk corridors we identify. This will bridge our theoretical setup with practical implications for urban planning and forestry management. Cell 3. In this cell, we're constructing a synthetic representation of the Charlotte area, including its suburbs, roads, and locations for trees, using a combination of NumPy and Pandas. The overall aim is to create a geographical and spatial model that can serve as a foundation for further analysis, perhaps related to urban planning or environmental studies. First, we define a bounding box that approximates the geographical limits of the area of interest, which allows any given latitude and longitude coordinates to be clipped within specific boundaries. This ensures that our generated data remains realistic and adheres to the geographical constraints of the region. Following this, we establish a data frame containing synthetic town centers, where each town is associated with its respective coordinates. Next, we create synthetic roads modeled as polylines. This structure is crucial, as it defines the connectivity between town centers and simulates real-world transport corridors. With highways, arterial roads, and local streets included, we make use of a helper function that generates slightly jittered lines between 2 points. This adds a layer of realism, avoiding overly simplistic straight paths. To further enrich the model, we allocate points representing trees along these roads, influenced by the type of road they are situated on. This process involves distributing a specified total number of tree points across the different road types, adjusting for the greater prevalence of trees near local roads compared to highways. Importantly, for each tree, we calculate its precise location by sampling points along the road centerline. We introduce variability in how far trees are placed from the road, generating both left and right offsets randomly, which enhances the natural feel of the placement. A critical part of this workflow is ensuring the various synthetic elements align well within our defined boundaries, which we've accounted for through the clipping function to prevent any unrealistic data points from emerging. And as we step into the next cell, we are likely to explore the potential implications of this generated data, perhaps focusing on how these urban features could relate to ecological or infrastructural analysis. This forward-thinking approach will enable us to dig deeper into the nuances of our created environment. Cell 4. In this cell, we are preparing to access actual zip code data, which is essential for understanding geographic distributions and demographic analyses. The availability of accurate zip code information can greatly enhance our analysis, particularly if we're looking to understand trends or patterns across different regions. Here, we're specifically looking at a dataset from the Census Bureau, which provides a reliable source of zip code information. The path indicated points to a downloaded folder containing this valuable data. It's important to ensure that the data is in the correct format and accessible from your script, as this will allow us to effectively manipulate and analyze it in subsequent steps. A key aspect to note is the URL provided, leading to the census data. This ensures that we are referencing the most updated and relevant information available, as demographic data can change frequently. As we set this up, we should keep in mind any potential challenges, such as file path issues or format inconsistencies, which can arise if the dataset is moved or renamed. Moving forward, the next cell will likely involve loading this dataset into our working environment, which will set the stage for further analyses. This will enable us to start querying and visualizing the zip code data, enriching our geographical understanding of the subject matter at hand. It's an exciting transition, as we'll soon be able to draw insights from the actual data we've gathered. Cell 5. In this cell, we're focusing on bringing together geographical data to enhance our understanding of tree distribution through zip code boundaries. This is a crucial step in spatial analysis, allowing us to cross-reference tree locations with their respective zip code tabulation areas, which will help in further geographic or demographic studies. First, we load the ZCTA polygons from a shapefile, which contains geographical boundaries for areas defined by zip codes. It's important to ensure the correct file path, and we're filtering it down to the necessary columns, specifically the zip code identifier and the geometry of the polygons. Converting this data to a standard coordinate reference system, EPSG 4326, ensures all our location data is uniform and can be accurately compared. Next, we create a geodata frame for the tree locations. This involves taking our existing tree data and generating geometric point representations based on their latitude and longitude. Specifying the same coordinate reference system guarantees that both the trees and ZCTA boundaries align perfectly in our spatial analysis. The heart of this cell lies in the spatial join operation. Here, we determine which trees fall within which zip code polygons. This is accomplished by using a left join, meaning we retain all tree data, regardless of whether they fall within a zip code area, while assigning the zip code where applicable. Renaming the resulting column for clarity allows us to work seamlessly with this newly joined data. We then merge this information back into our main data frame, enabling us to track which zip code each tree belongs to. After this, we check for any trees that weren't assigned a zip code, which could signify that they lie outside the ZCTA boundaries, presenting potential edge cases we need to address later. Finally, we display the first few rows of our updated trees data frame, giving us a glimpse into how this integration of geographic data has enriched our original dataset. Moving forward, we can leverage these zip code associations for further analysis, such as examining environmental factors or socioeconomic characteristics linked to specific areas. The next cell will likely build on this foundation, perhaps analyzing tree data by zip code to glean meaningful insights. Cell 6. In this cell, we are developing a risk model that assesses the probability of storm-related failures impacting trees, particularly in relation to roads and power lines. This is a crucial step in understanding how environmental factors contribute to potential hazards, allowing us to prioritize actions for risk mitigation. The process begins with several transformations applied to our dataset of trees. By calculating various risk factors based on their proximity to roads and power lines, we can quantify the level of risk associated with each tree. For example, the closer a tree is to a road, the higher its risk score becomes, while health metrics of the tree also influence its risk profile. We then create a weighted logistic regression model. This model takes into account several significant variables, such as distance to roads, branch overhang, tree health status, root damage, trunk diameter, lean angle, soil saturation, and wind exposure. Each of these variables is assigned a weight that reflects its importance in predicting failure. The Logit formula combines these metrics, transforming them into a probability score using the sigmoid function, which converts the log odds into a value between 0 and 1. After calculating the risk probability for each tree, we categorize them into different risk tiers: low, moderate, high, and severe. This classification makes it easier to visualize and communicate the level of danger posed by each tree. We even summarize the counts of trees in these tiers, which can help guide operational decisions. It's essential to be mindful of the weights we've chosen, as they should reflect the realities of the environment we're studying. As we move to the next cell, we will likely look at methodologies for visualizing this data or implementing strategies to manage the trees based on the risks identified. This step will enhance our understanding and response capability towards storm-related tree hazards. Cell 7. In this cell, we're diving into a concentration analysis that evaluates tree risk by synthetic zip codes and neighborhoods. This analysis is vital because it helps us understand where the highest concentrations of risk are located, enabling targeted interventions and resource allocation. First, we use the group by function on the dataset containing trees to create two distinct summaries, one for synthetic zip codes and another for neighborhoods. In both summaries, we are aggregating various metrics related to tree risk. For each group, we are counting the total number of trees and identifying how many of those trees fall into specific risk categories based on risk probability. We define a tree as high risk if its risk probability is 0.40 or more, and as severe risk if its probability reaches 0.60. The analysis computes not just raw counts of these high-risk trees, but also gives us the mean risk across the group, as well as the percentage of trees classified as high risk. These calculations are essential, as they provide a nuanced view of risk distribution and can uncover patterns that might not be immediately obvious. We also sort both summaries by severe risk, high risk, and mean risk in descending order. This ensures that the areas most in need of attention appear at the top of our output, making it easier to identify priority zones. Following the aggregation and sorting, we display the top 10 entries from each summary, giving us a clear snapshot of the most affected zip codes and neighborhoods. It's important to stay aware of potential pitfalls, especially around interpreting the results. For instance, a neighborhood might have a high number of trees, but could still have a lower proportion of high-risk trees, which indicates a different kind of risk management issue compared to an area with fewer trees but a high percentage of risks. In the next cell, we will likely explore how to visualize this risk data, providing a deeper insight into the geographic distribution of tree health and risk levels, potentially translating these findings into actionable community strategies. Cell 8. In this cell, we're identifying high-risk corridors, which refer to specific road segments that contain a significant number of trees categorized as high risk. This is crucial for prioritizing areas that require immediate attention to mitigate any potential hazards posed by these trees, thus ensuring public safety and effective resource allocation. The process begins with grouping the tree data by road identifiers, including the road ID, type, and name. By employing aggregation functions, we derive important metrics like the total number of trees on each road segment and counts of high-risk and severe-risk trees based on defined thresholds. Specifically, a tree is marked as high risk if its risk probability is at least 0.40, and severe risk if it's at least 0.60. This breakdown allows us to gauge not just the quantity, but the severity of risks present on each corridor. Next, we compute a corridor risk score, which serves as a simple yet effective way to prioritize these roads. The particular weighting in the formula emphasizes severe risk by assigning it a heavier factor. Consequently, this results in a risk score that highlights corridors with more urgent needs for intervention. After calculating these scores, we sort the results in descending order, making it straightforward to identify the corridors that pose the highest potential danger. In the end, we take a closer look at the top 25 corridors, but we only display the first 10 for now. This will provide us with a clear snapshot of the most critical areas to focus our efforts. Moving forward, the next cell will likely delve into how we can visualize these corridors, perhaps using mapping tools to present the information more intuitively to stakeholders or decision makers. Cell 9. In this cell, we focus on generating tree locations that are realistically situated near actual roads in Charlotte, North Carolina, by leveraging the capabilities of the OSMNX library. This step is crucial because accurately placing trees in geographic analyses can significantly impact the reliability of subsequent environmental models or simulations. First, we initiate the process by importing necessary libraries like OSMNX, Pandas, and NumPy. The main objective here is to create a street graph representation of Charlotte, which allows us to analyze and manipulate road networks. We retrieve this graph, specifically tailored for vehicular navigation. Next, we convert this graph into a geodata-frame format that contains our edges, filtering out any that don't have valid geometries. Now let's delve into how we generate the tree points. We set a target number of trees and use a random number generator to select edges and sample points along those edges. For each chosen edge, we calculate a point that is evenly distributed along the road segment, utilizing a function that interpolates the line string. Each sampled point captures essential information, such as latitude and longitude, and references the road it's associated with. After we collect these points into a structured data frame, we introduce a bit of randomness to place the trees off the road to simulate a more natural distribution. This involves generating a distance and applying small random offsets in both latitude and longitude, based on the standard dimensions of a typical tree canopy. The transition from graph data to actual coordinates demonstrates an intersection of data science and geospatial analysis. Displaying the first few entries from our tree data frame will provide insight into the structure of our output, which includes geographic coordinates and attributes that link back to the roads. In the next cell, we'll likely examine how these generated tree locations can be used in environmental modeling or further analyses related to urban forestry, enhancing our understanding of green spaces in urban settings. Cell 10. In this cell, we're addressing a common issue related to how data is structured, particularly when dealing with lists. Our goal is to transform these lists into a format that many Python packages can more easily work with. This matters because clean and uniform data helps ensure accuracy when performing analyses or visualizations. The first step here involves defining a function called first or join. This function takes an input and checks whether it's a list. If it is, we extract the first element of that list. Alternatively, if the list happens to be empty, it returns the string unknown. This is particularly helpful for handling cases where data may be missing or not well structured. We also account for any NaN values with the same unknown fallback, ensuring that our data remains stable and avoids errors down the line. If the input is neither a list nor NaN, it simply converts the input to a string. Then, we apply this function to two columns in our data frame, specifically road type and road name. This operation helps us streamline the data structure by ensuring that any list entries are replaced with single, usable strings, making it more convenient for future processing. It's important to note that we're assuming that the first element is the most relevant information, which may not always be the case, so it's worth understanding the data context. As we move forward to the next cell, we'll likely build upon this cleaned up data to analyze or visualize it further, allowing us to delve deeper into our dataset. The groundwork laid here will make subsequent analyses more efficient and insightful. Cell 11. In this cell, we're creating an interactive map using Plotly to visualize the proximity of trees to various types of roads in the Charlotte area and its suburbs. This visualization not only enhances our analysis, but also allows us to explore the potential storm risk associated with tree locations relative to highways and byways. The first step involves importing the necessary library, Plotly Express, which is known for its ability to quickly generate interactive visualizations. We then proceed to create a scatter map, but it's important to note that we're downsampling our data to 2,500 trees for performance reasons. This means we're selecting a smaller subset of the full dataset to ensure that the map renders smoothly without overwhelming the viewer or the system. Within the scatter map, we specify key variables, such as latitude and longitude, for the tree locations, while the color coding distinguishes different types of roads. This adds a layer of context to our analysis, helping us to visualize how trees interact with their proximity to these road types. Moreover, the hover feature enriches the user experience by providing specific details, like exact coordinates, road names, and the distance from the trees to the nearest road when hovering over a tree location. Setting the map's zoom level to 9 offers a focused view that highlights both the trees and the roads, making it easier to spot trends or clusters. As we finalize the visualization, we update its layout to employ an OpenStreet mapping style, which is both appealing and user-friendly. One crucial aspect learners should consider is how the downsampling might affect the visual output and any conclusions derived from it, ensuring they're aware of the inherent limitations in drawing insights from a sample rather than the entire dataset. In the next cell, we will likely delve deeper into analyzing the insights gained from this visualization, or perhaps explore additional contextual factors that may influence storm risk assessments based on these visual patterns. Cell 12. In this code cell, we're creating an interactive map using Folium to visualize high-risk corridors and the most dangerous trees in a specified area. This visualization is crucial as it allows us to identify areas that may require immediate attention, both for road safety and tree management, ultimately aiding in decision-making for urban planning and maintenance. The first step involves defining a helper function that converts line geometries into a format suitable for mapping. This function transforms the coordinates of the road geometries from shapely objects to lists of latitude and longitude pairs. Next, we create a lookup dictionary that maps road IDs to their corresponding geometries, facilitating quick access as we build our visualizations. Following that, we initialize a Folium map centered on specified coordinates with a standard zoom level. The key part of the process is a loop that iterates over our top corridors. For each corridor, we retrieve its geometry and calculate its visual weight based on the corridor's risk score. Notably, we assign a thicker red line to more dangerous roads, while local roads are displayed in orange. Each line also includes a tooltip, providing essential information such as the road name and its associated risk metrics. After configuring the corridors, we focus on the trees that pose a severe risk. We filter for trees with a risk probability of 60% or higher, and use a sampling method to avoid overloading the map with markers. For each severe tree, we add a circle marker, which highlights its location in purple. This marker conveys critical information about the tree, such as its risk probability and proximity to nearby roads and power lines. In this process, one should be mindful of the sampling step, as too many points may clutter the map. This careful balance allows for a more readable and informative visualization. As we conclude this cell by saving the map to an HTML file, we set the stage for the next cell, where we will likely explore how to analyze the data represented in this map, providing actionable insights based on the visual cues we've established. Cell 13. In this closing cell, we're wrapping up our exploration of the entire Jupyter Notebook, which is essential because it helps us summarize the insights we've gained and solidify our understanding of the material we've covered. This step not only provides a sense of closure, but also emphasizes the journey we undertook through the various analyses and visualizations. As we conclude, it's beneficial to reflect on how the different components we explored all fit together. Throughout the notebook, we examined distinct datasets, applied various methodologies, and generated visual representations that deepened our insights into the underlying phenomena. Each step was designed with a purpose, addressing specific questions that arose from our analysis. It's crucial to note how these components, like the data preparation, the exploratory analyses, and the final visualizations, play a cohesive role in building our understanding of the topic at hand. By consolidating our findings, we can better appreciate the key takeaways. This not only reinforces what we have learned, but also prepares us for further investigation. As we transition to the next part of our learning, we should consider how the insights gathered here can inform future projects or analyses. The groundwork we've laid will undoubtedly prove beneficial as we dive into more advanced concepts, expanding our toolkit and analytical capabilities even further. In the upcoming sections, we will build upon the knowledge from this notebook, exploring how to apply these insights to more complex scenarios and possibly introducing new methodologies for innovative problem solving. This leads us into an exciting phase of discovery, where we once again engage with the data in fresh and intriguing ways.